2014 Canadian Open Mathematics Challenge Part C. A sequence of the form T1, T2 to Tn is called geometric if T1 is A, T2 is AR, T3 is AR squared, and so on. For example, 1, 2, 4, 8, 16, and 1, negative 3, 9, negative 27 are both geometric sequences. In all three questions below, suppose T1 through T5 is a geometric sequence of real numbers. Part A, T1 is 3, T2 is 6. Determine the value of T5. T1 is 3 and T2 is 6. So this is my A and this is my AR, as they have described there. And they want me to find T5. So this is T5. And this is going to be AR squared, AR to the power of 3, AR to the power of 4. Well, I can use these two terms to figure out my R. AR over A is R. And then in terms of numbers, it's 6 over 3, which is 2. So my R is 2. And if my R is 2 and A is 3, then I can easily figure out AR to the power of 4. AR to the power of 4, A is 3, R is 2 to the power of 4. So that's 3 times 16, and that's 48. So T5 is 48. Part B. If T2 is 2 and T4 is 8, determine all possible values of T5. T1, T2, T3, T4, and T5. So again, we have A, AR, AR squared, AR to the power of 3, AR to the power of 4. And they tell me that T2 is 2, so this is 2, and T4 is 8, so this is 8. Okay, so very similar to before. AR to the power of 3 divided by AR is basically R squared, and in terms of numbers, it's 8 over 2. So that means R squared is 4. So R is equal to plus or minus 2. So now we can figure out, what do they want us to figure out? T5. Okay, so obviously I will need to figure out the value of A. Well, from here, A times R is equal to 2. So if R is equal to 2, that means we have A times 2 is 2, so that means A is 1. If R is negative 2, then we have A times negative 2 is 2, and therefore A is negative 1. So now we can figure out our values of T5. So T5 is AR4. When we use A equal to 1 and R equal to 2, that will be basically 2 to the power of 4, which is 16. If we use A equals negative 1 and R is negative 2, that will be negative 1 times negative 2 to the power of 4, which is negative 16. So 16 and negative 16 are the possible values of T5. Part C, if T1 is 32 and T5 is 2, determine all possible values of T4. So similarly, again, we've got T1, T2, T3, T4, and T5. And this time they have given me that T1 is 32 and T5 is 2. Okay, so this was AR squared, AR to the power of 3, and AR to the power of 4. So let's do this now. So AR to the power of 4 over A is equal to R to the power of 4. And in terms of numbers, that's going to be 2 over 32. So R to the power of 4 is 1 over 16, and therefore R squared is 1 over 4, but plus or minus, right? And therefore R looks like it's going to be negative plus or minus a half. Yeah. Okay. So A we have to figure out A. What do they want us to figure out? T to the power of T4, actually. Okay, so T4 is A R to the power of 3. Well, A we know is 32. And then R, well, we have two possible values for R. Either it's a half or it's a negative a half. If it's a half, it'll be a half to the power of 3, which is 32 over 8, which is 4. If it's negative a half, this will be 32 negative a half to the power of 3, which is 32 to the negative over negative 8, and that's negative 4. So there you go. Those are the two values for T4 for part C. The line L given by 5y plus 2m minus 4x minus 10m equals 0 in the xy plane intersects the rectangle with vertices 0, 0, 0, 6, 10, 6, 10, 0 at D on the line segment OA and E on the line segment BC. Show that M is between 1 and 3 inclusive. All right, so 5y plus 2m minus 4x minus 10m is equal to 0. So 5y, we can isolate if you want. 5y is equal to 2m minus 4x plus 10m. But actually it would be minus like that. So we can write it as 5y equals 4 minus 2m x plus 10m. Any way you want to write it, really. Okay, so my D, according to what they have written, if I draw a little diagram here, we've got 6 approximately here, 10 approximately there, and therefore we've got this little rectangle. And they're saying that there's this line that kind of cuts like this. So this is my D and this is my E. So that means that D looks like it could be anywhere from 0, 0 to 0, 6. And then E, similarly, it looks like it could be anywhere from 10, 0 to 10, 6. So those are sort of the boundaries for D and E. Okay, so let's figure out what we get here for each of these. So using this equation, let's put in the boundaries and see what we get. So when D is 0, 0, we will get 0 is equal to 0 plus 10m. So that means m is 0. This is when D is 0, 0. Okay. And then when we substitute 0, 6, this point, we will get 5 times 6 is equal to 0 plus 10m. So m is 3. So this looks like m is between 3 and 0. Now we have to figure out the same sort of thing, but this time for E. And this was, of course, for D equals 0, 6. Okay. So when E is 10, 0, again using the same equation, what do we get? We get 5 times 0 is equal to 4 minus 2m times 10 plus 10m. So that 0 is equal to 40 minus 20m plus 10m. And therefore 40 is equal to 10m. M is equal to 4. And then very similarly, when E is 10, 6, we have, again, in this equation, 5 times 6 is equal to 4 minus 2m times 10 plus 10m. 30 is equal to 40 minus 20m plus 10m. And therefore, this will be, well, let's see here, 10 is equal to 10m, and therefore m is equal to 1. So 4 and 1, so from that, we get that m is between 4 and 1 inclusive. So now we have to combine these two and get a common range. And it looks like the numbers that are common to both are m is between 1 and 3. And that is pretty much what they wanted us to figure out right there, wanted us to show. Show that the area of the quadrilateral ADEB is a third the area of quadrilateral OABC. So, as before, we've got this sort of scenario where you've got this line, and they want me to show that ADEB is 1/3 the area of OABC. OABC, okay. All right, so let's see what happens here. Well, the full OABC, that's just a rectangle, and since this was 6 and this was 10, that means the dimensions are just 6 times 10. So that's 60, and divided by 3, that's 20. So if we can show that the area of ADEB is 20, we pretty much have solved the question. All right, so let's go back and remind ourselves of the equation. It was 5y is equal to 4 minus 2mx plus 10m, right? That was the equation of that line, this line right here. That is presented by this line that passes through D and E. Okay, so working with that equation, we need to first find out some of these points. So E, for example, that has the x coordinate 10, that I know for sure. So I can substitute 10 into here to figure out the y coordinate. So 5y will be 4 minus 2m times 10 plus 10m, and therefore 5y is equal to 40 minus 20m plus 10m, and that means y is going to be 8 minus 2m. So put that in here, 8 minus 2m. Okay, in a very similar way, D, I can figure out the coordinates. The x coordinate is 0, so I just have to put 0 into that equation. So that's going to be 0 plus 10m, so therefore y is equal to 2m. So that's pretty straightforward. That's just 2m. Okay, I think now we're ready to figure this out. If I draw a parallel line there, I can do this. This side is 10, and then from here to here, that's going to be 6 minus this guy. So this dimension right here is 6 minus 8 minus 2m in brackets. So that's going to be 2m minus 2. So that rectangle, that area, ADEB, is essentially that rectangle plus this triangle. So basically just draw it in. The rectangle is just length times width, which is 10 times 2m minus 2. Okay, the triangle, okay, that's going to be 1/2 base times height. The base, again, is 10. The height, however, is this. So that is, let's see here, that is going to be this point, which is 8 minus 2m, minus this point, which is 2m. So that basically becomes 8 minus 4m. So 8 minus 4m is the height. 1/2 base times height. Okay, I think we got it. So let's multiply this out. So that's going to be 20m minus 20. And this is 5 times 8, which is 40. And then 5 times minus 4m is minus 20m. So look at that. The 20m's cancel. 40 minus 20 is 20. So we just proved that ADEB is 20, which is what we needed to prove to show that it's 1/3 the area of OABC. Determine in terms of m the equation of the line L parallel of the equation of the line parallel to L that intersects OA at F and BC at G, so that quadrilaterals ADEB, DEGF, and FGCO all have the same area. All right. So again, we're going to go back to that diagram. And again, so this time we've got this line situation like this. We got two parallel lines. Make them look parallel. And let's label this. This is A, O, B, and C. And then this is D. This is F. This is E. And this is G. Like that. Okay. So what do they want us to figure out? They want us to figure out the equation of that line. So the equation of this line right here. The one that goes through F and G. All right. If I can get 2 points, then I should be able to do this. The coordinates of F, well, that should be 0 and something. Something I don't know, so I'll just call it B. And the coordinates of G, well, that's going to be 10 and something. And that's something, again, I don't know. So we'll just leave it blank for now. All right, so the total area of this whole rectangle is 6 by 10. OABC is 6 by 10, so that's 60. And they're saying that these quadrilaterals ADEB, which is this guy, DEGF, which is this guy, and FGCO down here, those are all equal, same area. So if that means that each of them has an area of 20, since total is 60. Okay. So as always, the equation of a line is in the form y is equal to mx plus b. Now they're saying that this line is parallel to that line. If that is the case, then it has the same slope as DE. And DE, if you recall, was of the form 5y is equal to 4 minus 2mx plus 10m. So this was the slope. So that is going to be the same slope for this line, since those two lines are parallel. So my new equation is going to be y 4 minus 2mx plus some b. What that b is, I don't know, but we'll calculate what that b is. But we got to be careful because this has to be isolated in terms of y. So it's really y is equal to 4 minus 2m over 5x plus 2m, like that. So the slope is actually 4 minus 2m over 5. So just make sure that you make it consistent like that. Okay, now let's try to figure out b by subbing it some points on FG. Well, the first point right here, when x is 0, y is b. So when x is 0, you just plug that in and you get y is equal to b. And it kind of just worked out that way by coincidence. So I was right with my 0b. I had a hunch and it worked out. So okay, that's one good coordinate. Now let's figure out this coordinate over here. That's when x is 10. When x is 10, it'll be 4 minus 2m over 5 times 10 plus b, like that. And this looks like y is equal to 10 divided by 5 is 2, so that's going to be 8 minus 4m plus b. So this is 8 minus 4m plus b, the y coordinate there. Okay, so now all we have to do is just figure out the actual value for b in terms of m. And we can do that with the formula for the area. Okay, so the area of FGCO is 20. So 20 would be the area of that rectangle, this guy right here, this rectangle, plus the area of this triangle right here. Okay, so we got area of rectangle plus the area of the triangle. Okay, so 20 is equal to, okay, so the rectangle would be base, which is 10 times height, and the height looks like this b, right? So 10b. Okay, that's pretty good. Now the triangle is 1/2 base times height. The base again is 10. The height this time, we got to be careful. It's this minus that. So that's 8 minus 4m plus b minus b. So 8 minus 4m. 8 minus 4m is the height, this height right here. So 8 minus 4m. Okay, so we got 20 is equal to 10b plus that 10 divided by 2 is 5. So 5 times 8 is 40. So 40, and then 5 times 4 is 20, so minus 20m. So let's see here. Let's isolate here. 20m minus 20 is equal to 10b. And therefore b looks like 2m minus 2. So this is my equation, and I just have to put b there. So y is equal to 4 minus 2m over 5. That's the slope, x plus b, and my b, I just figured out, was 2m minus 2. So they wanted, in terms of m, as they show there, the equation of that line. And this is the equation of the line in terms of m. A local high school math club has 12 students in it. Each week, 6 of the students go on a field trip. Jeffrey, a student in the math club, has been on a trip with each other student in the math club. Determine the minimum number of trips that Jeffrey could have gone on. Well, we have Jeffrey and we have 11 other students. And we have to take into consideration that each trip has 6 students, and that basically means Jeffrey and 5 other students. Now, since Jeffrey goes on trips with each of the other students, he must go on 11 over 5 trips. Now, whatever the integer value is. So 11 over 5 is 2.2. So the integer value is got to be rounded up here because he can't go on 2.2 trips. So he's got to go on at least 3 because it's got to be at least 2.2. But obviously that doesn't make any sense. So 3 trips. So let's figure out what this really means. So let's see. Trip 1. Trip 1. Let's say the first 5 students, S1, S2, S3, S4, and S5, and Jeffrey. So that's 6 students, right? Trip 2, so the other 6 would be S6, S7, S8, S9, S10, and Jeffrey. And then trip 3, I guess we have to just put S11, and then Jeffrey, and then any 4 other students. And if you do that, it would match the criteria that Jeffrey has been on a trip with each other student in the math club, S1 through S11. So that's pretty much all that is. If each pair of students have been on at least one field trip together, determine the minimum number of field trips that could have happened. Okay, so we just figured out that each student must go on at least 3 trips, right, in part A. Now, there are 12 students. Since there are 12 students, that means there's 12 times 3, which is 36 total trips. But 6 students attend each trip. So that means we have 36 divided by 6, which is 6 unique trips. Okay. All right, so let's try to figure this out here. I'm going to make a list here. Trip 1, trip 2, trip 3, trip 4, trip 5, and trip 6. And then before I fill that out, I'm going to put the combinations because they're doubling up, right? There's pairs of students now. So the combinations are S1 and S2, that's 1, S1 and S3, S1 and S4, S1 and S5, and S1 and S6. This is just the list of pairing. Another pairing, S2 and S3, S2 and S4, S2, S5, S2, S6. And then S3 with S4, S3 with S5, S3 with S6. We got a few more, S4 with S5, S4 with S6, and then finally S5 with S6. These are the, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We got 15 pairs. And we have to assign them in these trips in a way so that each pair of students have been on at least one field trip together. Okay, so we have concluded that it's 6, but I want to show it so that it makes sense as to how this can be done. Okay, so let's start adding these. S1 and S2, let's put that here. S1 and S2. S1 and S3, we're going to put that there. S1, S4, we'll put that here. S1, S4. S1, S5, I'll put here. S1, S6, I will put here. Okay, so those S1 has pretty much been assigned. Now we have to start putting in the other ones. S2, S3. Well, I can't put it here because S2 has already been placed in trip number 1. So S2, S3. S2, S3. I can't put it here either because S3 is there, but I can put S2, S3 here. S2, S4, I can put here. S2, S5, I can put here. Okay, so S2, S6. S2, S6. Where can I put? I can put S2, S6 here. There we go. Okay, I've only got a few more left. S3, S4. Let's see here. S3, S4. I can put that here. S3, S5. S3, S5. I'll actually start utilizing this. I haven't done anything here. S3, S5, that can go there. S3, S6. S3, S6, and T4 because S3, S6 can fit there. Okay, great. Now we're down to S4, S5. S4, S5 I can put here. That would match. S4, S6. S4, S6. I can put that here. And then S5, S6. I can put that here. S5, S6. Okay. And then the remaining, we got some slots remaining here. We want to fill them up. And I guess we can just put extras, anybody. So this one, I guess we would put, we've already used 1, 2, 3, and 4. So S5 and S6. Like that. These are just extras. For here, 1, 2, 5, and 6 have already been used. So S3, S4, they can go on trip number 5. And then the last one, we've used up 3, 4, 5, and 6. So S1 and S2. So this right here shows very nicely that each pair of students have been on at least one field trip together. And we are shown that this is possible with 6 trips, where 6 is the minimum number of trips that needs to happen for this to occur. A polynomial f at x with real coefficients is said to be a sum of squares if there are polynomials p1x, p2x, until pnx, with real coefficients for which f at x is equal to p1x squared plus p2x squared plus pnx squared. For example, 2x to the power 4 plus 6x squared minus 4x plus 5 is a sum of squares because it equals x2 squared, x2 plus 1 squared, 2x minus 1 squared, root 3 squared. Determine all values of a for which f at x, x squared plus 4x plus a is a sum of squares. Okay, so we basically have to show that x squared plus 4x plus a is equal to something squared plus something squared, right? By definition. Okay, so let's see if we can do that. X squared plus 4x plus a. Most likely going to have to complete the square. So x squared plus 4x, take that coefficient 4, take half of it and then square it, add it and then subtract it, and then don't forget that a. That allows you to factor that, and that becomes x plus 2 all squared, and then this is a minus 4. Okay, now because these are sum of squares, right, this will always be positive, because when you square a number, regardless of what that number is, it will end up positive. So the sum of squares will also be positive. So this whole thing has got to be greater than 0, greater than or equal to 0. So what that means is that x plus 2 squared is greater than or equal to a minus 4. But if you just look at this right here, x plus 2 squared is already positive. So that means this also must be positive. So we can really conclude that a minus 4 is greater than or equal to 0. So a is greater than or equal to 4. That's a pretty good conclusion. So I think we pretty much got it already. I mean, if you look at this, this is pretty much in this form. If we bring this down here, we already have the x plus 2 as a square. And then to make this into a square, all we really need to do is just take the square root of it and then square the whole thing. And that's it. And this is true if and only if a is greater than or equal to 4. So that's pretty much part A. Part B, if we have f at x is x to the power of 4 plus 2x to the power of 3 plus a minus 7 times x squared plus 4 minus 2a times x plus a, if that is the sum of squares, for such values of a, write f at x as a sum of squares. Okay, so we've got this x to the power of 4 plus 2x to the power of 3 plus a minus 7x to the power of 2 plus 4 minus 2a x and plus a. Okay, so one thing, if you were to notice that if you plug 1 for the value of x, you actually get 1 plus 2 plus a minus 7 plus 4 minus 2a plus a, and that is 0. So that means 1 is a root. So that means x minus 1 is a factor. So this can actually be factored very nicely. 4 minus 2a x plus a into x minus 1. And if you do long division, you can get the remaining part of the equation, which is going to be x to the power of 3 plus 3x squared plus a minus 4x minus a. And then in this, if we say that's g at x, again, if you put 1 again into g at x, you'll get 1 plus 3 plus a minus 4 minus a, and that is also 0. So 1 is a root of g at x. So that means this equation can further be factored. In particular, g of x has 1 as a root, so you can factor out another x minus 1, and the remaining part will be x squared plus 4x plus a. Okay? All right. And of course, because it's the sum of squares, it has to be greater than or equal to 0. So this really is x minus 1 squared and this guy. Well, this guy we showed in part A, right up here, is already a sum of squares. Remember? That's the exact same formula. So that was already a sum of squares, which we had concluded was x plus 2 squared plus a minus 4 square root all squared. So you just put it in. And then when you multiply it all out, you get x minus 1 times x plus 2 all squared plus x minus 1 times the root of a minus 4 all squared. And there you go. You got a sum of squares. And again, if and only if a is greater than or equal to 4, because that was the condition from before. And that is f at x. And there you have your sum of squares.